Hello. So today we are going to be discussing correlation. So this video is going to be getting into correlation. I know throughout the semester on all the tests, one of our questions has been correlation does not imply what? Now we're finally getting into the reason why correlation does not imply causation. So let's get cracking. So correlation, here we go. So again, like I said, we've only mentioned about 1,000,000,000 times that correlation does not imply causation. So it's just saying that what this means is that when you're dealing with correlation, the variables that you're looking at, you can't say that, oh, this is causing something else. You're just saying they're related in some way. So to say, if you remember back from exam 1, there was the pissed inventory, the pretty intense screaming and shouting. I forgot what the ED stood for, but it's just a made up inventory in case you didn't know. But as scores increased on this anger inventory, aggressive driving behaviors also tended to increase. That is the language that is used with correlation. It has no implications of how it's causing it. Like in the next bullet point, it says next correlation, or not correlation, is higher scores on the pissed inventory, anger inventory cause drivers to engage in more aggressive behaviors. Correlation will never use the word cause or leads to or anything that would imply that one thing is causing a change in the other, but rather they're both increasing or decreasing together at some rate. There's a relationship there, but it's not a cause and effect relationship. So with correlation, what the hell is it? So it's actually a statistical procedure, as everything has been up to this point in statistics, but it's used to describe the strength and the direction of a linear relationship between variables. Now, this might not make much sense right now, but I'm going to show you some scatter plots, some graphs to kind of show you have a little more visual about it. But just to kind of get into more of what correlation is, there aren't any groups that you're comparing. Not in the same way that you would like a t-test for like let's say an independent samples t-test. If you also remember this example where we provide people with a laptop and pen and paper, and we have them take notes on a lecture, let's say an hour-long lecture, and we're going to compare and we give them an exam after the fact. After they take notes on the lecture, they take a little quiz or an exam about the lecture material and see how well they did. And we're comparing the scores between people who took the notes using a laptop, just typing them out, versus people who wrote them by hand. When we have groups like that, when we split the groups in half where, oh, half of you are going to use a laptop, half of you are going to take notes with pen and paper, that is a t-test. You have two separate groups of people, the laptop note takers and the longhand note takers, and you're comparing the average test scores or exam scores or quiz scores, whatever, between them. But instead, in correlation, again, we're not separating the groups down the middle saying half of you do this, half of you do that. That's a manipulation. We don't have manipulation in correlation, but rather we're just taking all the responses to one variable and comparing it to all the responses of another. So since we're not manipulating anything with correlation, you can kind of think of correlation as having two dependent variables. Again, we're not manipulating anything. We're not saying you're going to have a laptop, you're going to have pen and paper to take notes. It's just we provide some sort of questionnaire or survey or what have you, and it is just we're looking at their responses, but we're not really manipulating anything to have them respond a certain way, or we're not manipulating anything and expecting there to be some change. So we use scatter plots to graph correlation so we can visualize it. Each data point represents the intersection of the first and second variable. I'm sure you've seen scatter plots before. They look like this. So this is the data here, the units taken and the sanity levels. Now the units taken, you guys are familiar with how many what a unit is, and I'm sure you guys all know how many units you're probably approximately taking this semester or how many you've registered for next semester. But we have units taken, and then we have sanity levels, where I mentioned here that sanity levels is measured on a 1 to 5 scale, where 1 is not sane at all and 5 is very sane. So 5 is very like, oh, you know, everything's okay. And the lower you score on that sanity levels questionnaire on that scale, the less sane you tend to be. So you're not doing too great if you have a 1. You're not sane at all. Anyway, so what you'll see here is that, you know, for each column or for each row here, the units taken 6, sanity levels 5, that represents one participant. And you can think of it as we provide people with a questionnaire of some sort, and we ask them, how many units are you taking currently? And they'll say, oh, I have 6. And then we provide them a second question of, oh, on a scale of 1 to 5, how would you rate your sanity? Where 1 is not sane at all and 5 is very sane. And they say, oh, I'm very sane. That's a 5. Okay, cool. So then we graph that. So for each individual row here, we're graphing that on a scatter plot. So just to stick with this 6 units taken and 5 sanity level, we see units taken here on the x-axis, the horizontal axis. So 6 is about right here. Their sanity level is registered at a 5. So sanity level is over here on the y-axis. So here's that first person right here with the 6 approximately right there, and the 5 right there. And this is done for all of the remaining participants. So again, each row represents one person responding to these questions. So this first person, oh, I am taking 6 units and I'm pretty sane right now. I have a 5 on this scale. Next person is taking 18 units and they are saying, I'm not too good right now. I'm gonna score my sanity level as a 2. And you'll see the corresponding scores for each individual. Notice though that with correlation, we're simply asking how many units are you taking? We did not manipulate that as the researcher. We're simply asking them a question and they're providing us the answer. We didn't say half of you guys are gonna be taking more than 12 units and the other half are gonna be taking less than 12 units. Nothing was manipulated. We just straight up asked, how many units are you taking? The same thing for the sanity levels. We did not manipulate the sanity levels there. We just, again, simply asked them to provide their response to how sane are you on a scale of 1 to 5, where 1 is not sane, 5 is very sane. We're not manipulating that by any means. We're just asking a question and they provide the answer. So that is how we have a difference between a t-test where we're dealing with groups and we're splitting those groups or they're split in some way, and a correlation where we're simply just asking questions, not splitting any groups up, not manipulating anything, not separating people into high and low units taken or high and low levels of sanity or what have you. It's just, here's a question, I need you to respond to it. We're not manipulating anything. Okay, so I've kind of been talking about this, but comparing correlation to what we've done lately. Now, we've been doing a lot of t-tests. We've also done ANOVA, but ANOVA is essentially just 3 groups to a t-test as opposed to 2. But anywho, so with t-tests, let's say that we're going to be comparing people who do text and don't text during class. And then we compare the means of their exam scores. So for people who are not texting, here are their exam scores here with an average of 81. And the people that do text, where they say yes, here are their exam scores and they have an average of 76. Okay, so we're splitting them into groups here. We have the people who do text and the people who don't text. We as researchers have split the groups. Now, we might not have necessarily manipulated that, but we have still split them into 2 separate groups that we're comparing across, the yes texters and the no texters. Now, with correlation, we have to kind of form it a little differently. So again, each row represents one person. I've just labeled the participants as A through J because we don't really ask names. That's not really confidential. We don't need their names for this. But we're measuring 2 factors or 2 variables, the number of texts they send in class and their exam grades. So you see participant A sent no texts during class and they got an 88. Participant B, 4 texts and an 80. C, 6 texts and 78, you'll see down the row. So we're looking at how the changes in one variable are related to the changes in the other. So we'd kind of say, my hypothesis would be, I'm gonna say, I'm hypothesizing that the more texts that someone sends during class, the more likely it is that their exam scores would be lower. Now note my phrasing there. I'm not saying the more text you send is going to cause you to have lower exam grades. It's just saying, the more text you send, the more likely it is that your exam grade would be lower. It's really kind of cut and dry, or it's very persnickety in terms of, watch your phrasing. But with correlation, we're not doing any sort of manipulation. We're not splitting any groups of any sort. We're just asking them to provide us information. How many texts did you send in the last class period or whatever? And then what was your exam grade? We didn't manipulate anything. We didn't do any of that. We're not splitting them into, yes, you do text, or no, you do not text in class. It's just, how many texts? What's your exam grade? So there are two different things that correlation does. The first thing it does, it describes the pattern of data points for the values of two factors. So it's essentially talking about the strength and the direction. And I'll go more into that later in terms of the pattern that it follows. That follows into the strength and direction aspect of correlation. And there's a way to measure that. And it's so similar to Cohen's d as to how there's thresholds, but I'm getting ahead of myself. The second thing that correlation does is determining whether this pattern of the relationship between these two variables in your sample is present in the population in which the sample was obtained. So this is a null hypothesis test. Keep in mind that with null hypothesis tests, we're using the information that we have from a sample, be it 100 people, and we want to see if this if we're going to reject the null hypothesis or retain it. Remember that when we're dealing with samples, the purpose of us retaining or rejecting any null hypothesis is for us to say, hey, this is not present in the population, or this is present in the population, this relationship that we're seeing within our samples. So it follows that same guide, it follows that same idea, that same principle for correlation. We're also trying to see if the relationship between these two variables, be it number of texts people send and their exam scores, or number of Big Macs they eat and their happiness levels, whatever the two variables are that we're comparing, we want to see if this strength and direction of the relationship between them is present not only in our sample of 50 or 100 or however many, but also the population as a whole. So if we take a sample of college students, we want to see if this relationship we find within our 100 sample of college students, or 50, or again, whatever our sample size is, we're trying to determine if this is also present in the population of college students. Otherwise, we're just wasting our time. So I talked about how correlation measures the pattern, and it's examining the pattern that's present between two variables in the previous slide. Well, here's how we determine that pattern, by looking at the strength and direction. And this is determined by Pearson's R. So again, this is looking at a linear relationship between variables. Again, correlation deals with a linear relationship between variables. So we're looking at the strength and direction. So in terms of numbers here, if you remember, Cohen's d does not have a limit to how high it can be. It's a measure of how many standard deviations apart two groups are from each other. Well, there could be, theoretically, there's really no limit. They can be 1,000,000 standard deviations apart. Now, you're not likely to find that, but in theory, they could be. For Pearson's R, with the correlation coefficient, I'm just going to call it Pearson's R, but know that it is the correlation coefficient. It only ranges from -1 to +1. So you can calculate Pearson's R, and again, get everything from negative to +1 and everything in between. But if you see a Pearson's R that is -1.5, it's garbage. If you see a Pearson's R that is 2.2, it's garbage. Pearson's R can only be as low as -1 and as high as +1. There is no wiggle room there. Okay, so the direction, I'm going to talk about the strength and direction about Pearson's R, but I'm going to start with the direction. Now, keep in mind that with Pearson's R, with the strength and direction of a correlational relationship, the relationship between two variables, we're trying to see how they vary together, how they rise and fall together, and how strong is that likely to happen. So we're starting with the direction. This is determined, you can tell direction immediately by looking at the sign of your Pearson's R. If it's negative, like a negative 1.0, a negative 0.5, a negative 0.25, that would be a negative relationship because Pearson's R is negative. If you have a positive Pearson's R, be it R equals 1.0, R equals 0.45, 0.2, 0.8, whatever. If it's positive, you have a positive relationship. If your Pearson's R value is negative, you have a negative relationship. So unlike Cohen's D, where it didn't really matter in terms of the signage, 2.2 or negative 2.2 for Cohen's D, it really doesn't make any difference. It's still saying you're about 2.2 standard deviations apart. With Pearson's R, the direction, the sign, the negative or positive is important. So with a positive correlation, when your R value is greater than 0, because 0 implies no relationship, but when your R value is greater than 0, between 0 and 1.0 and 1.0, because keep in mind it can't be any higher than 1, you have a positive relationship. So this means that as values for one factor or variable, as values for one of your variables increases, so too does the other. So they rise together or they go down together. But whatever the other one does, whatever one does, the other is likely to follow. That is a positive relationship. They'll both increase together, they'll decrease together. It's a positive relationship. You got two variables working in the same direction. Just like any, good relationship, if you're working together, you go together. When your R value is negative, that is a negative correlation. Again, these are all referring to the direction, a positive or a negative direction. And it's just referring to the direction in which the variables are going. So with a positive relationship, they're both going up or going down together, but they're both heading in the same direction. And with a negative relationship, with a negative Pearson's R, as one increases, the other is decreasing. So that's, maybe if you've had unhealthy relationships or just not the greatest in your life, you might notice that while you're going to school, attending, classes or whatever, your partner might be, trying to, bust their SoundCloud and trying to share their Fire SoundCloud. Anyway. So as one variable is increasing, the other is decreasing. They're actually heading in opposite directions. That is a negative Pearson's R. And again, that happens. You have a negative Pearson's R. You have a negative correlation when your Pearson's R is negative. It's pretty simple to point out. So this is just a visualization of what positive and negative Pearson's R is. So again, when you're positive, it's when your R is greater than 0 and, but greater than 0 and up to 1.0. And that's when your factors or your variables are increasing or decreasing together, but they're both going in the same direction for positive. And negative is when where one variable is increasing, the other is going in the opposite direction. So the other is decreasing. And that is just when R is less than 0 and, no lower than negative 1.0. Okay. So the direction is pretty easy to determine. Is it positive R or negative R? Boom, you have your direction for your correlation there. The strength is referring to how consistently scores for each factor change. So how strong or weak is the relationship that as one variable increases, the other tends to increase on a fairly similar level, or if it's a negative relationship, as one variable increases, the other decreases on a relatively similar level. So the strength is determined by the number. So where the directionality of correlation was, do you have positive or negative? The strength is referring to just the number itself. So if you have a 0.5 or a 1.0 or a 0.25, the strength is referring to the number itself. Now this is similar to Cohen's D, how it has a threshold. And also when you're determining strength of correlations, you don't worry about the positive or negative. You're more so just looking at the number itself. So if we have thresholds just like we do for Cohen's D, except they're a little different for Pearson's R. If it's 0.1 and below, you have a small effect. You have a small effect size. You have a weak strength or small strength, whatever. Weak, small, they just mean the same thing in this case. But if it's 0.1 and lower, then it's a small effect. And this also applies to negatives. So again, if you have a negative 0.05, that's still a small Pearson's R. Now, a medium strength Pearson's R is if your number is between 0.1 and 0.5. So if you have an R value of 0.35, that is a medium strength relationship for your Pearson's R. And then if it's 0.5 and above, if the number itself is 0.5 and higher, that is a large or a strong effect size for your Pearson's R. Just to reiterate, keep in mind that these are for the numbers itself. If you have a Pearson's R value of negative 0.9, that is a strong or large effect size. Even though on this chart, it's saying, oh, well, it's less than 0.01, it's negative 0.9, so that would be small. That's not true. It's just the number, and 0.9 is a very strong, a very large correlation. It's has a strong effect size. So again, just to reiterate the strength of it, only pay attention to the number, because the signage, the positive or negative, that refers to the direction, not the strength. Okay. And when your Pearson's R is equal to 0, that means there's no relationship. Okay, so just as a visualization, here are some positive relationship scatter plots. So when R is greater than 0, but again, no higher than 1, because that's the highest it can be, this is what those scatter plots look like. So I'm not sure if you can see the line on here. It's pretty weak. It's pretty faint on this PowerPoint, but I'm again going to post it on Canvas so you can see it in greater detail. But you'll notice that a perfect positive correlation of 1.0, it's just a straight line. You can see here that it's just 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. It's a perfect straight line. We don't often get perfect correlations when we're looking at research in psychology. Doesn't happen all that much. But just know that a perfect positive relationship of R equals 1.0, if we were to graph that on a scatter plot, it's just a straight line. Positive relationships, you'll notice that the excuse me, that the dots, the plots on the scatter plot are actually going in an upward direction, starting from the bottom and going to the top, from left to right, I should say. So going to the next one over, and where R is equal to 0.66, you'll see that they're not really perfectly on that line. You can't draw a straight line and hit every single point like you could for the Pearson's R value of 1, but rather they're huddled. There's a line about right there, and that line is just the closest line to, the line we'll discuss more with linear regression, but essentially that line is just a line that represents wow, I cannot speak. So the line is just trying to get as close to all of the data points as possible, and a straight line that is, as close to all the data points as possible. So with R is 0.66, you'll notice that they're not really all on that line perfectly like they were for 1.0, but they are still huddled relatively together, as opposed to R is equal to 0.8, 0.08, I should say, excuse me. You notice that the lines are just kind of all over the place. I find that it's easy to think of the weaker the relationship of your Pearson's R, so again, this 0.08, they're just kind of all over the place. It's like if you were to take a shotgun, shoot a wall, like from a far back distance. Wow, from a distance, when you shoot a shotgun, it kind of tends to scatter. It just kind of spreads. That's sort of like a weak relationship when you plot it on a scatter plot for Pearson's R. It's just kind of all over the place. It doesn't really follow a linear pattern, doesn't really huddle close to each other, kind of like you see for 0.66, and definitely for 1.0, you see them huddled in a straight line. The weaker the relationship, the more that instead of following a straight line, the weaker the relationship is, the more those plots tend to kind of spread outwards. Negative relationships, you'll see that where positive relationships go from the left to the right, they go up. Negative relationships from the left to the right, they go down. So you'll see that, again, this perfect negative correlation is just, boom, straight line between all of them. Here's negative 0.53. Again, this is considered a strong relationship because the number itself, that 0.53, is greater than 0.5. So that is a strong relationship. So you'll see that they're still kind of huddled together. Here's the line right here. So they're decent, they're pretty close to it. And again, that is a strong relationship. And then over here with Pearson's R is equal to negative 0.12. That's considered a medium relationship because it's between 0.1 and 0.5. But it's still, you know, you'll see that it has a little bit more of a shotgun scatter there, where it's a little further apart than you see here for negative 0.53 and definitely for negative 1.0. Okay, so group collaboration time, I'm just going to go through these. So you want to determine the strength and direction for each of the following Pearson's R correlations. So that first one of R equals 0.4, well, that is a positive strength because the number is positive. And the direction of it, or positive direction, sorry, the strength of it would be considered medium because it's between 0.1 and 0.5, that number itself. Going forward on to the next one, R is equal to negative 0.8. Well, we know that the direction of it is negative because it's a negative Pearson's R value. And the strength of it, just looking at the number itself, 0.8 is certainly larger than 0.5. So that would be a negative strong correlation. 1.0, that's positive, and that is quite strong. That is indeed a perfect correlation. R is equal to negative 2.0. Well, the direction is technically negative, but that does not make sense. Pearson's R can be no lower than negative 1.0 and no higher than 1.0. So that R equals negative 2.0, that's actually not a true R value. That is actually a mistake or just trash. So that R is equal to negative 2.0, nothing, because it can't be any lower than negative 1. Okay, so moving on, R is equal to negative 0.2. Again, that's a negative direction because it is a negative Pearson's R value. And the strength would be medium because the number itself, that 0.2, is greater than 0.1 but less than 0.5. So it's in that medium range. And then finally, R is equal to negative 0.5. That's a negative direction and a strong or large strength because it is 0.5. So that is the threshold for the median, or that's the threshold for having a strong or a large Pearson's R value effect size. All right. So of course, we're going to be calculating Pearson's R. Now, I'm only going to go through this once because I'm not going to ask you guys to calculate Pearson's R by hand. More so what I'm concerned with when it comes to Pearson's R is for you to interpret the strength and the direction of it. So what I've gone over thus far, how, you know, the positive and negative indicates the direction and the number of Pearson's R itself is indicating the strength. That's more so what I want you guys to know because you're not going to be calculating Pearson's R by hand for probably any class at this point. But I do still want to show you guys how it's done so you have some idea of the conceptual, you know, basis of Pearson's R of correlation. So here's the formula. So R equals sum of squares for x and y divided by the square root of the sum of squares for x times the sum of squares for y. And I have that written out in English here so you guys, you know, can kind of have an idea of what the hell all this is saying. Okay. So that's our formula that we use to calculate Pearson's R. Now, what that is saying is R is equal to the covariance of x and y. So covariance is just this, this little Venn diagram here where they vary together. Okay. Hence, you know, how they overlap for this Venn diagram. The covariance of x and y is where they overlap, where they kind of go together at the same time. And we're dividing that by the variance of x and y separately. So that's what that formula is. That's essentially what the Pearson's R formula is. We're taking how much the scores vary together and dividing it by how much the scores vary separately. The larger the covariance, the larger that they work together, the larger the more that they vary together, the stronger the relationship for Pearson's R is. Again, regardless of if it's positive or negative, that we're not worried about. That doesn't indicate strength. But the larger the number itself is for Pearson's R, the more they will vary together. Okay, so I've taken the example from several slides ago, asking people with the example of asking people, how many units are you taking? And then how would you rate your sanity levels, with 1 being atrocious and 5 being bitchin', really good. Here is the data. These are the same numbers from before. I'm just going to show you guys how to calculate Pearson's R from that. Okay, so you notice that this table here has some information. So we have all of our units taken, every individual person's units taken, how many they stated, and then the corresponding sanity levels there. This M of X down here is just the mean of X. So X is representative of our units taken, Y is representative of our sanity levels. Down here, we have the mean, so we're adding all of these together and dividing by the total number of cases, aka participants, which is 1, 2, 3, 4, 5, 6, 7, 8. So we just took the mean of these 8 units taken and got 13.38. And then we did the same thing for the 8 sanity levels. We added them all together to find the mean, and we have a mean of 3. Okay, so for the deviation scores here, this is taking each individual X value, so 6 minus the mean of X, which is 13.38. So for this column, we're going to be doing 6 minus 13.38, 18 minus 13.38. Again, just each individual score for the units taken, X is having 13.8 subtracted from it. And we'll do the same thing for the Y. So just to show you guys, we have 6 minus 13.38. Again, each individual score of X, 6 minus the mean of X, which was calculated here at 13.38. So 6 minus 13.38, 18 minus 13.38, 20 minus 13.38, and down the line. We did the same thing for the deviation scores for Y, for our sanity levels. So the mean was 3. So we're going to take each of our individual sanity level scores, the 5, 2, 1, 3, 2, 4, 4, 3, and subtract the mean of 3 from them. So 5 minus 3 is 2, 2 minus 3 is -1, etc. Okay, so now we have each individual deviation score. So I've just kind of taken out all of the formula here just to give us the basic number. And now we're going over one column, and now we're getting into the sum of squares portion. Okay, so here we're taking the value we got for taking individual scores of X. So each individual mean, or each individual units taken minus the mean of the units taken. And we're multiplying that by each individual sanity level minus their sanity level mean, which we've already calculated already. So here we take, for this row, it's -7.38. So this X minus mean of X times Y minus the mean of Y, 2. So here what you're doing is just multiplying these two numbers together for each row. So -7.38 times 2, 4.62 times -1, 6.62 times -2, and down the line. And that's giving us that's the sum of squares for X and Y. So we're going to add these all together, and that gives us a -41. Okay. Now, the next one. So this, again, this sum of squares for X, Y is just -41 because we've added all these together. And since we're dealing with a lot of negatives, then we have that. So now we are doing the X minus mean of X squared. So again, we've calculated all of these. We have, all right, -0.738. Again, look at this. It's this column. So this column squared for each row. So we have -7.38 squared, 4.62 squared, 6.62 squared, etc. And that's giving us all of these. We'll add those together to get the sum of squares. Again, we're adding 54.46 plus 21.34 plus 43.82, blah, 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 blah. And that gives us 157.84. Okay. We'll do the same thing for y. Now we're doing just these numbers squared to give us all the numbers in this column. So 2 squared, -1 squared, -2 squared, etc. And we add all those together to get the sum of squares for y. Again, this is the y variance, this is the x variance, and this is the covariance of the two together. Okay. So we've done all the calculations that we need, and it's tedious. It's similar to calculating variance by hand. If you remember when we calculated variance by hand, that feels like ages ago. But it kind of follows a similar pattern, because think about it. When we look at Pearson's R, it's taking the covariance of x and y, the covariance of our two variables, which in this case are the number of units taken and the sanity levels. And then we are comparing that we're dividing that by the variance of x and y separately. Cool. Okay, so here we are. Now, bringing back that formula, the sum of squares for x and y, which was -41, which we got by adding all of these together, dividing it by the square root of the sum of squares for x, which is this column here. We added that and got 157.84. Times 12, which was the sum of squares for y. Again, we got that by doing the same thing, just squaring all these numbers and adding them together. Now, just following down the line, so you multiply 157.84 times 12, 1894.08, find the square root of that, 43.52. Now we have -41 over 43.52, and that gives us a value of -0.94. Whew. So our Pearson's R value is equal to -0.94. So in fact, the relationship between the number of units taken and sanity levels indeed has a strong negative correlation. Again, it's negative because it's a negative Pearson's R value. It is a -0.94. And we know that it is strong, or large if you prefer to go it that way. It is a strong Pearson's R value because the number itself, that 0.94, is greater than 0.5. So it's indeed strong. All right. So what does this mean? So when we're saying that there's a strong relationship, a strong negative relationship between the number of units taken and the reported sanity levels, again, keep in mind that a negative relationship is saying as one thing goes up, the other is tending to go down. So with a negative, strong Pearson's R relationship, we see that the more, let's say, the higher number of units that you're taking tends to tends to have a decreased level of sanity level. So again, keep in mind that sanity levels, the lower that you scored, the less sane that you are. So a 1 is saying, dude, I'm going crazy. So the more units you're taking, the less likely it is that your sanity levels, the sanity levels for you are going to be that great. So as your units taken increases, your sanity levels tend to decrease, which makes sense. You know, the more stress you have, the more units you're taking, it's implied that you have a lot more stress, a lot more workload, and your sanity levels could possibly decrease in relation to that. So it makes sense. All right. Now, I talked about how Pearson's R, the purpose of correlation is to not only observe the pattern of relationships between two variables, but also determine if the relationship that we're seeing in our sample is indicative to that of the population. Can this information we have, can this -0.94 be applied to the population? Can we generalize this to the population? And of course, this is where significance testing comes in. So first, our step one is, hey, what is our null and alternative hypothesis? So for Pearson's R, for correlation, we're not using mu, we're not using any sort of, we have another Greek letter because of course we do. It kind of looks like a ever so fancy P, but this is the Greek letter rho. So the null hypothesis is saying that rho is equal to 0. Remember, when Pearson's R is equal to 0, that means there is no relationship. So it makes sense to say, oh, the null hypothesis is saying the null hypothesis states that rho is equal to 0. There is no relationship. Units taken The number of units you're taking has no relation to the sanity levels in the population. And then for our null hypothesis, we're saying that rho does not equal 0. Units taken is related to sanity levels. There is some relationship in the population there because the rho value is not equal to 0. Or you can think of it as Pearson's R is not equal to 0. Okay, so step 2, we're setting the criteria. So again, it's two-tailed because it does not equal 0. And it's alpha set at 0.05 because that's just how we roll. Now, to determine the degrees of freedom, we're using degrees of freedom again because we're dealing with samples primarily. We don't have a population in particular that we don't have a predetermined population that the information is provided for us. So we're using degrees of freedom, similar to how we did for all sorts of t-tests. We're dealing with samples here strictly. So our degrees of freedom is equal to our sample size minus 2. So remember that for each person, we had 8 participants in our example of units taken and sanity levels. So 8 people responded saying, oh, I'm taking 6 units and my sanity levels are a 5. And each individual person answered both of those questions. We had 8 people doing that. So to determine our degrees of freedom, we just take our number of participants of 8 and we subtract 2. Our degrees of freedom is equal to 6. Boom, cool. So we are going to use a table to determine our critical values. Now, since Pearson's R can be positive or negative, just keep in mind that our critical values can also be positive or negative, similar to t-tests. The only time when your critical values are not positive and or negative is for a ANOVA, because that's an analysis of variance. It's only positive. Anywho, so this is a different table to find the critical values. This is a Pearson's R table, not a T table, so this is different. But you'll see here that our level of significance two-tailed tests right here. Oh, okay, 0.05. And then we have our degrees of freedom is equal to, n minus 2. So we determine our degrees of freedom to be 6. So we just follow the line here, and I've circled it to make it easier on all of our eyes. So our critical values for this test, for this null hypothesis test for correlation, is plus and minus 0.707. Nifty. Okay. Now, our test statistic, we've already calculated that. Remember that our Pearson's R value was negative 0.94. So we've calculated step 3 already. So we have our Pearson's R value of 0.94. Now step 4 comes up where we make a decision. So now we're comparing our Pearson's R value to our critical value. So since our Pearson's R value is negative, we're going to compare it to our negative critical value. If it is less than the negative critical value, we reject the null hypothesis. So negative 0.94 is indeed less than negative 0.707. So we're rejecting the null hypothesis. So that's telling us, just like how in step 1, where we stated in sentences, oh, the null hypothesis states that number of units taken is not related. And if we reject the null, then the number of units taken is related. Boom, that's what we're concluding here. The number of units taken is related to sanity levels in the population. Nifty. All right. So that is Pearson's R. Again, what I want you guys more so to take moving forward, what I want you guys to take from this lesson moving forward is maybe not so much how to calculate it. You know, though, that it's comparing the covariance, how they vary together, and dividing it by how they vary separately. And if you have a large enough number, the more they vary together, the more they change together, be it in a positive or negative direction. The stronger the relationship is between those two variables. They're moving up and down, or up and up, or down and down at a relatively similar rate. So that is Pearson's R. But again, I want you guys to be able to interpret Pearson's R through the strength and direction. So what does it mean when you have a negative Pearson's R? What does it mean for the variables when you have a positive Pearson's R? What is the strength of Pearson's R? What's the threshold? Determine the strength and determine the direction. That is more so what I'm looking at for Pearson's R. And also know that, of course, correlation does not imply causation. All of this, we're not doing any manipulations. We're not saying, oh, you know, units taken is causing you to have lower sanity levels, or the more units you're taking, it causes you to have lower sanity levels. We can't make that conclusion with Pearson's R, with correlation, because we're not manipulating anything. We're not forcing people to take more or less units and compare their sanity levels. It just simply is. And so when it simply is, we cannot imply causation from that. So thank you very much. That is all I have to say about Pearson's R. Again, if you have any questions, always be sure to contact me through email, or however, if you want to email me for a Zoom meeting, that's fine. But just make sure that, you know, if you do have questions, to let me know. And I will do my best to answer them, but I'm going to answer them. So got you. Thank you.